Driving is pretty awesome. Maybe you already have your driver's license, or maybe you're waiting for that day. But when the day comes, it comes with a cost. You gotta fill up your gas tank. And that cost is pretty high these days. Let me give you a tip. If you want to save some money, don't get a really massive car. A really massive car takes more gasoline. Why? Well, the more mass something has, the harder it is to accelerate. That's actually exactly what Newton's second law tells us, that force is equal to mass times acceleration. So if you get a car with less mass, you can accelerate it with less force and use less gasoline. So for example, a gas-powered scooter gets 70 miles to the gallon, whereas a huge truck, maybe like 10 miles to the gallon. So let's all save some money at the gas tank and learn about Newton's second law. Let's start by reviewing our lesson objectives. First, we'll explain Newton's second law. Then we'll contrast weight and mass, which are two commonly confused ideas, but in Newton's second law, it's really important to get them straight. And lastly, we'll solve some problems using Newton's second law so you get really comfortable with this equation. Throwing a small stone is easy. You can do it without any thought or effort. But when the stones get bigger, it's not the same story. At some point, you need a big machine to help you. Why? Again, it's Newton's second law. It tells us that the force needed to accelerate an object depends on its mass. The more massive the object, the harder it is to accelerate. Let's take a look at the mathematical expression for Newton's second law. It tells us that the net force is equal to m, which stands for mass, times a, which stands for acceleration. What exactly is this net force thing? Let's remind ourselves. Well, net force is just all the forces added up. So we're not thinking about one force on an object, but all the forces added up on an object. Okay? So Newton's second law tells us that the net force, all the forces added up, are equal to mass times acceleration. But what exactly is mass? Well, mass is a measure of the total matter present. It's just a way to tell us how much stuff is there. And because of that, mass doesn't change. So this space shuttle is high above the Earth, where the gravitational pull of the Earth is still there, but it's less. So it's actually lighter, which sounds like less massive, but it's not. The amount of stuff that's there didn't change. It still has the same number of atoms and molecules, the same amount of steel. The mass doesn't change. Just as much stuff is there. And so if I want to accelerate it, I still need a force. If I want that space shuttle to go faster, I'm going to have to turn on the thrusters. This mass contrasts with weight. Weight is a force due to gravity. So it's on the force side of Newton's second law. And weight definitely changes. Weight does change. This astronaut on the moon might weigh just 20 pounds. And that's because the acceleration due to gravity on the moon is much less. And with that lower acceleration comes a lower force due to gravity. So weight does change, but mass doesn't. All right, back to Newton's second law. It tells us that the net force is equal to mass, which is, remember, how much matter is present, how much stuff is there, times a, which is acceleration. This tells us that the greater the force, the greater the acceleration. And we can express that with a special mathematical expression. We got this a, which stands for acceleration, and then this weird little fish-like symbol. That's the proportional to sign. And so we read this as acceleration is directly proportional to force. That directly part means that as acceleration increases, force increases. Let's think about that. Here we have a jet plane with two jet turbines that generate a huge force. That force is so high, what will it do to its acceleration? Does it give it a high acceleration or a low acceleration? You guessed it, a high acceleration, because there's so much force. Contrast that with a single prop plane. Here there's less force. And because there's less force, what will that do to its acceleration? That's right, there's less acceleration. Okay, returning then to Newton's second law. We come back to this thing over and over again. Now we want to think about the relationship between mass and acceleration. First, we're going to put mass on the other side of the equation. We're going to divide it over to the left-hand side. Notice now that that means mass is on the bottom there. Okay, that's called the denominator, and the bigger I make that m, the smaller acceleration is going to get. And we have a special way to express that. Acceleration is proportional to 1 over mass. Acceleration is proportional to 1 over mass. Another way to read that is as acceleration is inversely proportional to mass. That means as mass goes up, acceleration goes down. So that 1 over m thing there is really important. It makes mass inversely proportional to acceleration. Let's give you some examples. Let's say here that we have a tractor trailer. It has high mass. There's a lot of stuff there. And because of that, if it wants to accelerate, it's going to generally have low acceleration. On the flip side, if we take something like a motorcycle, which has low mass, what is going to be true of its acceleration? Is it going to be capable of high acceleration or low acceleration? You guessed it, high acceleration, because it doesn't have much mass. Okay, we've thought about this thing qualitatively now. Let's actually map out the forces and think about the net force. Here we have a car that's accelerating. It's going to speed up. Its velocity will increase. And remember that for an object speeding up, the applied force is greater than friction. And that means that we now have a net force. Let's map the forces out on our car. First, we'll start with the normal force, which points up, and gravity, which pulls down. They're actually in the vertical direction. The forces perfectly cancel out. If they didn't, it would be falling through the earth or lifting off the earth's surface. And so those cancel out. And what we really want to think about is the right and left forces. The engine is pulling that car to the right. So that's the force of the engine. The last force to consider is what? Friction, that's right, and it resists motion, so it's going to be pointing the opposite direction. Should the arrow be bigger or smaller than the force of engine? It should be smaller because it's accelerating. Because it's accelerating, the force from the engine must be greater than the force of friction. Now let's just focus in on those horizontal forces, friction and the force from engine. And we're going to write a net force expression. The net force, remember, is all of the forces combined. So the net force is equal to the force of engine, and then we need to take into account friction. Should we add friction or subtract friction? Well, because they're pointing in opposite directions, we should subtract it. Friction is reducing the ability of that car to accelerate. So the net force is equal to the force of the engine minus the force of friction. Again, we've used those vertical lines here, which means we're thinking about the magnitude and not worrying so much about the direction, other than that it tells us to subtract. Now, one other important thing to see here is that in every single spot we see force, we can plug in mass times acceleration. So we could plug mass times acceleration into the net force, into the force for engine, or the force for friction. And that's what we're often going to do when we solve problems. This problem tells us that a car accelerates at 12 meters per second squared and that it has a mass of 950 kilograms. We're told that the force of friction is 850 newtons. What is the force from the engine? Okay, let's start by drawing a free body diagram. We know we have our car, and that pulling that car forward is the force of our engine. Meanwhile, resisting that motion and pulling backwards is the force of friction. And we actually know the magnitude of the force of friction. We know what that's equal to. So let's list the variables that we have. We know that the friction force is 850 newtons. We know the acceleration of the car is 12 meters per second squared. And we lastly know the mass of the car, which is 950 kilograms. Listing out the variables we have is always a good first step in solving our problems. Now, we're going to move on to writing the net force equation. The net force equation tells us that the force net is equal to the force of the engine, which pulls it forward, minus the force of friction, which resists that motion. These are all magnitudes, so I can put my vertical bars here to remind myself that these are magnitudes of forces. Okay, next, what am I going to do? Well, I don't know the net force, but I do know the mass and acceleration, and remember that Newton's second law tells me that force is equal to mass times acceleration. So I'm going to go ahead and use that to replace my net force with mass times acceleration. And that's equal to still my force of my engine minus my force of friction. Let's go ahead and solve for what I'm looking for. What am I looking for? Well, recall that we're asked what is the force from the engine. So we're looking for the force from the engine here. So I'm going to go ahead and I'm going to solve for the force of the engine by adding the force of friction to both sides. Okay, that's going to give me mass times acceleration plus the force of friction is all equal to the force of my engine. Now I'm ready to plug in the variables that I have. I'm going to plug in 950 for mass, 12 meters per second squared per acceleration, plus the force of friction, which is 850 newtons. When I go ahead and plug in 950 times 12, I'm going to get 11,400, and then I'm going to add 850 to that, and I'll get 12,250 newtons is equal to the force of my engine. Okay, so that's how I can use Newton's second law and consider also friction to solve for the force of an engine or anything in my net force equation. Okay, let's go ahead and move on and do one more problem. A plane with 4 propellers accelerates with a force of 3,000 newtons. If the force of friction is 1,200 newtons, what is the force due to each propeller? Okay, so here what we want to figure out is the force of each propeller on this 4-prop airplane. Let's draw a nice big free body diagram. So we'll make it nice and large, and the reason is because we want to represent each of the 4 propellers. So there's 1 propeller, 2 propellers, 3 propellers, and 4 propellers, all pulling that plane forward. Okay, what's resisting the motion? That's the force of friction. So the force of friction is going to be pulling it back. Force of friction. And what's pulling it forward is 4 little force of propellers. Force of propeller, force of propeller, force of my propeller, and force of my propeller. Whew, all right, that's a lot. Now it wants to know what is the force of each propeller. Well, let's write down some things that we know from the problem. The total thrust and the net force is going to be 3,000 newtons. We're told that the plane is accelerating with a force of 3,000 newtons, so that's telling us our net force. And that might be a little more obvious once I draw the net force equation. We also know the force of friction. So the force of friction is 1,200 newtons. All right, let's go ahead now and draw our net force equation. We know that the net force is equal to the force of our thrust, which is all of those propellers. So we have the force of our propeller, but how many propellers do we have? We have 4, so we're going to put a 4 right there. And that's kind of what's new about this problem, is we're thinking about 4 identical forces pulling it forward. So we could just write force of propeller plus force of propeller plus force of propeller plus force of propeller, but we know it's much simpler just to write 4 times that force. And then what's pulling it back is our force of friction. So we'll write F sub F. Again, using those vertical bars there just to represent magnitude. So we're not really thinking about the direction other than the fact that the friction is opposed to the force of the propellers. We're going to plug in the magnitudes there though. Okay, what do we want? We want the force of that propeller. That's our unknown, right? And luckily our net force already has that there. So all we got to do is go ahead and solve for that force of propeller. So we're going to plug in 3,000 newtons into the net force is equal to 4 times the thing we're trying to solve for, minus the force of friction, which is 1,200 newtons. Okay, now we're going to add 1,200 to both sides to go ahead and get the force of propeller by itself, and we'll get 4,200 equals 4 times the force of our propeller. Last step of algebra to get it by itself is we're going to divide both sides by 4, and the 4's over here are going to cancel out, and we'll get that the force of our propeller is equal to 4,200 divided by 4, and that's 1050 newtons. Now, if we wanted to be real detailed, we would say, hey, guess what? We only had 1 sig fig there, so we would round that to 1 sig figs, which would actually be 1,000 newtons. So we're going to go ahead and write down our answer rounded to just 1 sig fig, which would give us 1,000 newtons. Okay, so that's the force from each propeller pulling that plane forward. Let's summarize what we've learned. We've explained Newton's second law, that it tells us that force is equal to mass times acceleration. We've also contrasted weight and mass. We said that mass is a measure of how much stuff there is, and weight is actually a force due to gravity. So weight changes while mass doesn't. Then we've solved problems using Newton's second law. We saw that we could set up net force equations and solve for how fast things are accelerating or what the force of friction is.
Hey, hey.